In this video, we're going to introduce the concept of an alternating series. An alternating series is any series in which consecutive terms have opposite signs. As an example of an alternating series, we've introduced this guy a couple times, but I wanted to introduce it one more time. The sum from n equals 1 to infinity of 1 over n is known as the harmonic series. If I were to take this same series and alternate every other term being the opposite sign as the previous term, so 1 minus a half, plus a third, minus a fourth, plus a fifth, minus a sixth, and so forth and so on, this would be known as the alternating harmonic series. Now, all alternating series will have some sort of alternator in there. Some people think that there's a strong connection between upper-level mathematics and cars because we have terms like manifolds and alternators and things of that nature. All I know is occasionally I change the oil and then I press the go pedal to go. Common examples of alternators, this is probably the most common one that you're going to see, is negative 1 raised to the nth power. When n is odd, this is going to be equal to negative 1. And when n is even, this is going to be equal to positive 1. So one possible representation of the alternating harmonic series would be 1 over n that is then multiplied by negative 1 raised to a power. Now with that in mind, if I were to say negative 1 raised to the nth power, then that would give me the opposite of the alternating series. N equals 1 would give me a negative 1. N equals 2 would give me positive 1/2. So on occasion, the way that we make sure that it is of the correct parity, parity is referring to whether something is odd or even, we could say the n plus 1 power. That way, n equals 1 will give us an even exponent, and n equals 2 will give us an odd exponent, and so forth and so on. So this would be 1 minus a half plus a third minus a fourth, and so forth and so on. There are other examples of alternators. For example, the cosine of n pi is known to be an alternator because if we were to plug in several values of n equals 1, the cosine of n pi would be the cosine of 1 pi, which is negative 1. Cosine of 2 pi is positive 1. The cosine of 3 pi is negative 1, and the cosine of 4 pi is positive 1, and so forth and so on. So this is another example of an alternator. This last one I think is a really pretentious example, but it still gets used from time to time. The sine of pi over 2 plus n pi. Now this basically works the same way as the cosine, except instead of using the left and right ends of the unit circle, it uses the top and bottom ends of the unit circle. So for n equals 1, 2, 3, 4, etc., n would give us cosine of 3 pi over 2, the sine of 3 pi over 2, followed by the sine of 5 pi over 2, then 7 pi over 2, then 9 pi over 2, etc. Now, as soon as you see a series that has an alternator in it, you can safely assume that it is an alternating series. So a great question to ask is, when does an alternating series converge? And for that, we have decided to give it its own special name. It is called the Alternating Series Test. Because it comes up from time to time, we will abbreviate it. This will be the AST for Alternating Series Test. So with that in mind, let's say that we have a series that we refer to as the sum of a sub n. If you remove the alternator, we're going to refer to those terms as b sub n. That is, of course, a fancy way of saying a sub n is equal to an alternator times b sub n. It doesn't necessarily have to be this. It could be one of the other forms of the alternator. The important thing is we want the positive versions of this. To determine the convergence of the alternating series, we need only consider the sequence that we get from this. So, consider the sequence of b sub n, where all of your terms in that sequence are greater than 0. If the sequence satisfies two conditions, one of them is that the sequence b sub n is decreasing, keeping in mind that we were talking about positive values only, and the sequence b sub n converges to 0. Then you can conclude that the alternating series converges as well. Now, the idea behind the proof of the alternating series test is the following. What I'd like to do is consider n along here and the partial sums of the series along here. So we have a first term. First term will have a certain value associated with it. So this point up here is going to represent the first term, or first partial sum of the series, which is the same as simply the first term. Now the next term is going to be subtracted, and it's going to be smaller than this, which guarantees that the second partial sum will be still positive, but it'll be greater than 0. So that'll be S2. So this gap right here represents the difference between those two consecutive terms. Now the idea is the difference between the next consecutive terms will be even less than that, and then to the next consecutive term will be even less than that. And then adding that term, and then subtracting that term, and then adding that term, and subtracting that term, essentially what's going to happen is as we go along, there will be a sort of, it has to stay in between certain quantities. However, those quantities are going to converge toward each other due to the fact that the sequence is going to converge to 0. So as soon as you have the first partial sum and the second partial sum of the series, you have essentially the upper and lower bound for the series itself. Now this is not nearly as important as the actual testing itself. So imagine for a second that I go to a restaurant and I say, I would like a steak. And I would like you to cook it well done, and I'd like you to serve it with ketchup. Well, then there is only one way that I'm not going to complain about my meal. It's that the steak better be well done and it better be served with ketchup. If either of those conditions fails, then I'm sending the steak back. Much in the same sense that if either of these conditions fails, then your alternating series does not converge. We'll go through that with a couple of examples. In fact, since we just talked about the alternating harmonic series, let's see if it converges. So does the alternating harmonic series converge? So we said just a moment ago that the alternating harmonic series can be set up as -1 raised to the n plus 1 power times 1 over n. Consider then the sequence of the non-alternator. So what we're saying is that b sub n is simply equal to 1 over n. We need to show two things about this. First one is we need to show that the sequence 1 over n is decreasing. From section 11.1, there are two different ways to do this. Take b sub n plus 1 and show that it is less than b sub n for all n greater than or equal to 1. So this is saying that 1 over n plus 1 would have to be less than 1 over n. Now this is true due to the fact that this denominator is larger while the two numerators are the same. So larger denominator means smaller fraction. The alternative to show that it's decreasing would be to consider the generating function, which in this case would be f of x is equal to 1 over x. Differentiate this function and show that it is going to be less than 0. The derivative of 1 over x will be -1 over x squared. This indicates always negative, this indicates always positive, this indicates always positive, so negative times positive divided by positive is guaranteed to be less than 0. So, two ways to show it is the algebraic method and the calculus method to show that something is decreasing. We also want to show that it converges to 0. We want to show that the sequence converges to 0. The good news is this is one of the very basic limits at infinity from back in Calc 1. So here's my well done steak. Here's my side of ketchup. Therefore, by the alternating series test, the alternating harmonic series converges. Now we don't need to know this at this point in time, but we're going to prove this before the end of the class, like within the next couple weeks. It actually converges to the natural log of 2. And we are going to prove why later in chapter 11.